I brought 12 fascinating facts that are shareable star stuff that you can share next time you're out under the night sky with anybody your friends or family with. So let's jump right into it. All right, so number one, if you didn't know, you can use your hands to tell the time. Your hands, together with the stars, can tell you the time, not the absolute hour like with a watch or even a sundial, but you can tell how much time has passed during the night. So all you need to do is hold your hand, your fist out at arm's length and raise your index finger and your little finger here like this and hold it out at arm's length. Let's see if I can do that. There you go. Looking at the sky. And this distance between them is 15 degrees on the sky. Now, we all know that 360 degrees makes up a circle. All the way around the circle is 360 degrees. So 15 degrees is just a small part of the circle all the way around the sky. And this is how much the stars move in 1 hour. So if you see a group of stars early in the evening, like the constellation Orion over here on the left, and you go out again later in the night, you can tell how many hours have passed by how many of these little 15-degree, I'm trying to put that up in the camera, 15-degree hand sections have passed between where the stars were and where you see them now. And if you want to know where a star that's lower in the sky right now will be when it will be overhead, well, it's just the number of hours as you count the 15-degree sections across the sky. And by coincidence, this just happens to be the same amount by which the moon moves toward the west across the sky from night to night. So tonight, if you look in the southwest and you see the moon halfway up the sky, then tomorrow at the same time, it'll be 15 degrees farther over to the west. Cool, right? Okay, so number two, how to tell a star from a planet. Now, there are 5 planets that are visible to the unaided eye: Mercury, Venus, Mars, Jupiter, and Saturn. And when you're looking up at the sky, unless you're using a telescope, the planets generally look quite similar to bright stars. In fact, if I didn't tell you, you probably wouldn't have known that one of these objects, these bright objects here, is the planet Saturn, and the other is the bright star Fomalhaut. There they are. But when you're actually out sky watching in person, the tip-off that you're looking at a planet and not a star is that stars tend to flicker, whereas planets tend to shine steadily. Now, this is because the stars are so far away that their light is really just a single point, a tiny point, and ripples in our atmosphere can easily cause our view of them to twinkle. Planets are much, much closer, being right here in our solar system. And when you see a planet through a telescope, you see a little disk or crescent. Many of you have probably seen Jupiter or Mars or even Venus. And this is a slightly larger area than a single teeny tiny point of light that's coming from a star very, very, very far away. And so that slightly larger area makes planets appear more constant in brightness than the stars, unless what you're looking at is very low near the horizon, in which case rippling air currents will cause pretty much any object to flicker. So it has to be a little bit above the horizon for this to work. Okay. So number 3, the planets are always found along a line that stretches across the sky. In this sky chart, you see 3 planets from the top right to the bottom there: Saturn, Mars, and Jupiter here, plus the moon down here at the bottom, arrayed more or less along this yellow line that stretches diagonally across the scene. Now, if you're out looking at the sky in person, it's more of an arc that stretches all the way over from the east, like what you see here. Imagine you're looking to the east and all the way up across the sky like an arc, all the way over to the west. This line is called the ecliptic, and essentially it represents the plane of the solar system. in which the planets orbit our sun. Now, specifically, it represents Earth's orbit. And the other planets' orbits are more or less within that flat circular plane orbiting our sun. So you can think of that line on this sky chart here. You can think of that line along which you find the planets as being something like the floor or the base of a merry-go-round. And the planets are like the other kids riding the merry-go-round along with us. All right, on to number 4. Talk about the moon for a few minutes. How far away is the moon? The moon is farther away than people often think. It can sometimes appear large in the sky, especially when it's rising or setting. But if you hold up a finger, back to using your hands here, if you hold up a finger at arm's length, and you'll find that it more than covers the moon. In fact, the moon is only half a degree wide. Now, remember from before, this distance between your fingers held at arm's length, that's 15 degrees. So the width of the moon is 30 times less wide than this distance on the sky. But the moon is a pretty large world, right? It's a quarter the size of planet Earth. So it's a pretty big place. So how far away is it to make it look that small in the sky? Well, a good ballpark number to keep in your head is that the moon is about 250,000 miles away, or 400,000 kilometers. That distance is so big that you could just about fit all the 7 major planets between the 2 worlds. So the moon is 250,000 miles away, which is really quite a distance. Okay, continuing with the moon. Next up is number 5. As we mentioned, the moon often looks bigger when rising or setting, and this is due to an illusion that's known as, creatively, the moon illusion. It's very well known, but not everybody understands. Most of us don't think about why it happens. The thing is, it's not that the moon is closer when it's on the horizon. It's actually a teeny bit farther away in space, so that's not it. And it's not an effect of the atmosphere magnifying the moon like a lens. That's not what's going on. Turns out this is a case where it's actually all in your head. It's a perceptual effect of human vision and the way the human brain processes visual information. There have been studies over the past 50 years seeking to explain what's going on, and it's still not 100% clear how it works. But the general consensus from people who study these things is that your vision system perceives things on the horizon to be farther away. The horizon, oh, that's a long way away. So when you see the moon rising there, that must be really huge. It's a big thing, really far away. And so you perceive the moon as a larger object at a greater distance. And that's the moon illusion. Pretty weird, but also kind of cool. Who doesn't love seeing a gorgeous, giant rising moon? All right, number 6. So here you see the phases of the moon as they appear to us in the northern hemisphere in the top row. Those are this month's moon phases. Actually, I took the numbers off. They're every month's moon phases. And these look like they're reversed compared to the appearance of the same phases for the southern hemisphere. From the northern hemisphere, we see the moon begin its cycle of phases each month as a crescent with its right side illuminated, and it fills up, becomes full, and then from the right to the left, and then becomes a crescent on the left side and then disappears as a new moon. But from the southern hemisphere, the moon still rises in the east and sets in the west like it does here, but it appears to fill up in the opposite direction, from the left to the right. Plus, the moon itself appears upside down compared to how we see it here. So why is that? Well, in the northern hemisphere, we tend to look toward the south to find the moon in the sky. If you think about it, you're usually looking kind of south, southeast, southwest to find the moon. But in points south, such as Australia, South Africa, Argentina, observers tend to look toward the north to find the moon. And so their viewing orientation toward the moon is reversed, like you see in this cartoon here. So what we see as the top of the moon, top to us, in our sky is the bottom of the moon for them in the south, and vice versa. And this flip of the moon's orientation also explains why the phases appear to proceed in the reverse direction as well. Okay, now number 7, I'm sure you're all familiar with this pattern of stars over here on the left. This is the Big Dipper, of course, which is part of the constellation Ursa Major, the Great Bear. Now, there's a lot of fun stuff, interesting stuff in this part of the sky in general, but I got 2 fascinating bits I'd like to share with you. First is that most of the stars in the Big Dipper are siblings. All of the stars, except the ones on the 2 very ends of the Dipper, these ones right here, all of these stars are found at around the same distance from Earth, and they're all traveling through space in the same direction. They're what's known as an open cluster, or an open star cluster, as opposed to a tightly packed globular star cluster. This open cluster of stars, they all formed in the same stellar nursery about 500 million years ago, and they're slowly going their separate ways as gravitational and other forces in the galaxy slowly pull them apart. And this is how stars tend to form in groups within vast clouds of gas and dust, and then they slowly separate over time. Now, our sun would have formed this way as well, and its own brother and sister stars are out there in the galaxy somewhere even now. And then there's more to one of these stars than meets the eye. If you look along the Dipper's handle, which is right here, right where it starts to bend, this little kink in the star, this in the handle, this one star here is actually not one, it's 2. The bright star is Mizar, and the dimmer one is called Alcor. The pair is very easy to see with binoculars, and some people with really good eyesight are able to separate them with just the naked eye. But even a low-power pair of binoculars, you'll be able to see it. Now, these stars are gravitationally bound together, so they're not, it's a true double star. They're not just kind of near each other in the sky for us, but really at wildly different distances in space. No, they're relatively near each other in space. They're associated. And even here, though, there's more to it than meets the eye, because Mizar is not just one star. It's a pair of binary stars. So it's 4 stars that actually look like one because they're so close together to us from very far away. It looks like one star, but it's 4. And it doesn't stop there, because Alcor was discovered to be a binary as well. So it looks like one star to most of us to our naked eye, but it's actually 6, right up there in the bend of the Big Dipper. Pretty cool. All right, on to number 8. It turns out that the role of North Star is not a permanent position, so to speak. You see here a photo that I took out in the Mojave Desert, not desert. There's a boulder here that's sort of pointing up to a bright star, this one right here. And that's Polaris, the North Star. And you probably know that if you locate it in the sky, it's right above the due north direction, and it can help you find your way, right? Well, here's what it looks like if you take if you have the camera snap the same photo again and again for like 3 hours, and then the sky turns overhead while the images are being taken, and you combine these photos using software, and you get star trails like this. Really pretty. These are fun to make and to look at. And what you'll notice is that there's a point here in the center of rotation. All the stars appear to be rotating around this spot. And that is called the North Celestial Pole. This is the point where a line straight up out of Earth's North Pole, at the top of the north part of the planet, if you had a line go straight up into space, that's where it would point to, the North Celestial Pole. And you can see this one bright star right here on the lower left side of the pole. That's Polaris. And so it's rotating around the pole as well. So it's not precisely on the pole, it's just very close to it. Now, you may have heard that while everybody knows Earth's tilted on its axis, right? But you may have heard that while it's tilted, it also wobbles, like kind of like a spinning top, over tens of thousands of years. And as it makes these wobbles, this point in the sky, the North Celestial Pole, actually wobbles in a circle as well with the rest of the planet. That makes sense that it would do that. So it points to other stars, other spots in space over long periods of time. And so some of those stars are brighter, some of those are fainter. They're not always Polaris, they're other stars. And so sometimes there's no bright star close to the pole. And that's currently the case for the southern hemisphere. There's no south star, so to speak, in the present epoch. And so that changes over time. Okay, keeping with the stars, stars have different colors. You may have seen this with your own eyes, but if you haven't, I encourage you to take a look. The colors depend on the star's temperatures and ages. And so they range in color from red to yellow to white to blue. And in this one photo, you see several different colored stars. Down here near the bottom center is if you've ever spent much time looking at the constellation Orion here, it's easy to find. The upper shoulder here on the left shoulder is the bright red star Betelgeuse. Very red, very easy to pick out. A little bit above it here in the picture, a little bit to the west of Orion in the sky, is the constellation Taurus. You can see the V-shaped face and horns of Taurus, the bull. And this bright red star is the eye of the bull, Aldebaran, also a very bright red star itself. Up to the north, over here to the left in the picture, is a very bright yellowish star known as Capella. It's a little oblong there because my camera lens is not the best in this picture, but I assure you it is a normal circular spherical star. Up here at the top of the image and near the center is the Pleiades, another open star cluster. The Pleiades, and those stars are distinctly bluish, especially in telescope images. You can see them here, they're bluish. And then another great one to look for, if you're looking at Orion, just look straight across Orion diagonally toward his right, I guess it's his left knee, our right side. This bright star here is called Rigel, and it is distinctly blue-white in color. And so you can see them in the same, without even moving your field of vision, the red and the blue in Orion. Very interesting. But ultimately, most of a star's characteristics, including what color it is, how long it will live, and even how its life will end, are determined by how much mass it starts out with when it forms. That is, how much hydrogen it begins life with. More massive stars are more compressed by their own gravity and thus heat up to a hotter temperature, with red being cooler and blue being hotter. But as stars go through phases in their life cycle, and a star, they do go through phases, excuse me, and you might have a star that begins its life as a yellow star or a blue star, and later in life it balloons to a giant size, and that causes its overall temperature to cool down. And this is what will happen to our own star, the sun, in a few billion years when it swells from a dwarf yellowish star to a red giant star late in its life. So we have that to look forward to, but don't worry, it's not going to be for a couple of billion years. I assume we'll have all gone on to other things by then. So number 10, just exactly how many stars can you see with the eye, the unaided eye without a telescope? Well, if you live in a big city like I do, it's not many. You're lucky to see a handful. This is a photo I took in my own neighborhood in Los Angeles, and you could only see 2 bright stars. There are a few dimmer, fainter ones here, but I can assure you I did not see them with my eye when I took this photo. I was lucky to see these 2. And this is because of light pollution. It's the collective scattered light from all the billboards and tennis courts and gas stations and everything that makes city life what it is. But if you head out to dark skies, away from the city, you'll see a lot more stars. This is a shot of my colleague Bill taking a photo out in Death Valley, where it's very dark. Beautiful skies out there. Now, as for how many stars are technically visible to the eye alone, estimates vary, but under dark skies, it's probably a couple thousand. So to do the math real quick, over the entire celestial sphere of space that surrounds Earth, there are perhaps 10,000 naked eye visible stars. And you can see half of those, the ones that are above your hemisphere of the planet, but you can really only see half of those at any given time because half of your hemisphere is in daytime, is in sunlight, and only half of it's in nighttime. Plus, you probably lose a bunch of stars that are really close and right along the horizon. So a rough estimate is somewhere around 2,000 stars on any given night are technically would be visible to your naked eye. But how many you can actually see depends on how dark your sky is, as we discussed, and really how good your vision is. So our penultimate shareable fact here is number 11. The Milky Way is our home galaxy, and it's seen edge on from within the spiral disk. I hope you've been fortunate enough to see the Milky Way with your own eyes. It's something I highly recommend because it's really awe-inspiring. To the eye, it looks like a misty, sort of a faint band of misty light that stretches across the sky, kind of like clouds. This photo, though, shows what's really there if your eyes could only capture a little more light, but it's impressive even to the eye. You have to go out to dark skies to be able to see it, though. Now, what you're looking at is the bright core of the Milky Way. This is the center of our galaxy. It's a disc-shaped collection of hundreds of billions of stars arranged in a spiral pattern. And you can see that shape in this upper image here on the upper right, which is an illustration of what we think the Milky Way looks like based on survey data of stars in our galaxy. And beneath it, this lower image on the right is a real photo from the Hubble Space Telescope, which shows a spiral galaxy, a different galaxy from ours, but another spiral galaxy all the same. And by comparing these three views, I think you can get sort of a sense, start to understand or appreciate the perspective that we have as we're looking toward the bright center of the galaxy from within the disk itself. Look, it's remarkable. I can't get it. I can never see it too many times myself. It's the kind of sight that makes you feel both very small, but also connected to something much larger than yourself, something truly cosmic in nature. And that brings us to our final stop, number 12. Most stars you can see are relatively nearby in space. The vast majority of stars you can see in the night sky are a few dozen to a few hundred light years away from Earth. And there are a few that are maybe up to a couple thousand light years away, but most are much closer to our region of space. So an ordinary smallish star like our sun is just not going to be visible clear over on the other side of the galaxy. You probably wouldn't see a star like our sun in the night sky. If it was up in the night sky, if it was more than 50, 60 light years away, it's just too faint. And that's the case with most of the stars in our galaxy. They're just too distant and too faint to see with your eye. But with a powerful telescope, you can see much, much fainter and more distant things. So this image is a great example. Only two of the objects you see here, these ones with the pointy spikes, there's one here and one down here, a smaller, fainter one. Only two of those objects in the image are stars within our own galaxy. Every other object in this image from the James Webb Space Telescope is an entire, incredibly distant and super faint galaxy of its own. And you can see they're just countless. And these incredibly distant, deep looks into the night sky, which are also deep looks back in time, help us understand how the universe around us evolved into the place we find ourselves in today. And I hope that next time you find yourself looking at the stars, you'll feel just as charged with wonder as I do. All right. So to wrap things up, where can you get skywatching resources? Well, we have a number of great products from NASA, and you can find lots of them at the link you see here at the bottom left, or go to nasa.gov and just search skywatching, all one word. You'll find our latest monthly highlights video, which I make. We also post that to NASA's social media. You'll find links to our daily observing guide, info on local astronomy clubs, and more. There's also a useful website and app for your mobile device called Spot the Station, which can help you know when and where to look for the International Space Station, which is always exciting to see, thrilling to see. And you can use NASA's Eyes on the Solar System to see the locations of the planets in 3D, get the sense of context of what you're looking at when you actually see them arrayed across the sky. There are also tons of resources from other organizations outside of NASA, and I'll just share a couple of personal recommendations now. These are not NASA endorsements, they're just things that I like to use personally. Starting with Stellarium there on the left, it's a free app you can get for your smartphone and on your laptop. It's pretty easy to use, and it shows you accurate sky charts for your location any day, anytime. I also like to use timeanddate.com. They have a few good resources for moon phases, eclipses, meteor showers, etc. And there are a couple of premier meteor organizations, including the International Meteor Organization and this site, which is the American Meteor Organization. And you can get good tips on meteor viewing from those groups. So those are just a few of the resources that I like to recommend personally. So that is it for our whirlwind tour of shareable star stuff. I hope I didn't move too fast for you to keep up, and that there are a few things in there you didn't already know, and maybe you feel like you might like to share with others. Again, you can see our skywatching tips every month on NASA's social media accounts. If you have a burning question that I didn't cover and we run out of time here, you can email me personally. There's my email address. And if you'd like to check out more of the night sky photos I take, some of them are for NASA, some of them are just for me. You'll find me on Flickr. So thanks for joining.